Now this example automates several, all but one component of the plant model test suite as proposed by IEEE P2000.2. The base model is Solar 5, and it's kind of derived from the Solar 4 model that you just showed previously with the average model versus the detailed model and the systematic fault application. Some differences though. So I did change on the source impedance. You'll see that it's a different, same angle, but 137.54 ohms. So it's a weaker grid. Over here, at the inputs to the power plant controller, those were some sliders and constant values before. In this case, we're taking data node inputs, so these are actually controllable signals. The fault, you'll notice, perhaps we're using different types, B and C. This is the last state it was left in. That fault type is going to be automated. And we also have some control pin inputs to the source. So these are new, the phase of the source, the frequency of the source, and the kV magnitude of the source. What we can do with the controllable source like that, we're not going to change the impedance, but source control, an option. It's under the configuration tab of the source, where source control, that we can put in external pins for all of those, the phase, the magnitude, and the angle. And you can see that if you click on the help button. The way these control signals are managed, you see there's 7 of them on the schematic, is through these table functions over here on the right, which are new. So there's a constant source. It's available, capitalized time. It's the output of the simulation time. And the one that is left doing something interesting is the power factor reference. Last time we ran it. Double click on that. It's an XY transfer function, but it's basically a table. And so I have different breakpoints in time. That's the X data. And then in the Y data, we're changing between unity power factor 0.95 back to 1 and then back to minus 0.95. And this is a script, PlantScript.py, that's going to automate everything. It is a few hundred lines of code long, so I'm just going to give a high-level overview. You'd have to read this to actually understand it. There are more component names that have to be defined. So fault and fault L and recorder were used before. Fault time. We need that because sometimes we want to apply the fault and sometimes we don't, so we have to change the time for that to happen. Solar lib, that's our library which has the solar plant model, and VSC AVM is the average model. We need to change things like control mode for that. So we need to change parameters for that. Grid is the name of the voltage source that we're going to change. And we're also having these table functions, the seven control signals that can change, with time, with simulation time. They all need names because I need to reprogram the tables. I have a fault lookup table. We're only doing 5 types of faults instead of 12, but still same idea. We're going to run different variations. We have different control modes. So for example, if I want to do control voltage, then I send POC_voltage to the power plant controller model, and you could see that if you edited parameters on the schematic, you would see that as one of the choices. So this kind of you can use that Python function that lists the parameters by name, and you can also right-click and look at parameters on the schematic and kind of figure out what's available to adjust. 2 different power values we wanted to use in different tests. 3 different fixed Q values, 2 different frequency values, and 22 different phase angle values. This next table, the step values, there's 4 control angle reference tests, and so for this first one, this is the voltage reference. It's going to start at 1 per unit, and then we're going to jump up, to 1.05 and then down to 0.95, and we're going to run that case for 50 seconds. We're going to do it with the 2 different power levels and different Q values. Okay, so Q doesn't change because it's in voltage control mode. We have the flat start model initialization tests. So there are 7 listed there for 1 voltage control, 3 reactive power control, 2 power factor control, and again, we're running that sequence of 7 for 2 power values, the ICR and then the Pmin. These are utility functions. Kind of remember from the default script, I did it all in one main function or one loop. But for different test suites, we need to turn that fault on or off. So there's a utility function here to set the fault type. This sets the nominal control of the reference signals so that they're not going to vary at all. They're just going to be a continuous signal with no step change. This is a function that simulates a flat start test. So we are setting different grid impedances. The fault time, 999.9, it's not going to turn on at all. The fault isn't going to be applied at all during the simulation. We can change the maximum time, Tmax, different scenarios. We run them for 10 seconds up to 50 seconds. So in this case, it's a 20-second test. And then for each power level, and then for each of those 7 variations, each of those 7 different control modes, we are setting first a reference value of the power. It's either Pmin or Pmax. And then for each of the 7 different control modes, we're setting a flat control, depending on whether it's real reactive power or power factor that we're trying to control there. I won't go through all these in detail, but there's a function for each one of the test suites. So the undervoltage ride through, we're setting different parameters. Here we're setting the fault type is it's not going to be 0 anymore. The fault is going to be applied. So that is done up here. The time of the fault is 10 seconds and the duration is 0.16 seconds up here. And we're setting that, the grid impedance to be the weak grid condition. The overvoltage ride-through tests, we're setting the control modes of the IBR here. We need to program the source. So between 10 seconds and 11 seconds here, the voltage goes up to 1.2 times kV and then it goes back to 1 times kV. And we're doing that at different control modes for voltage. Reactive power, but the voltage set point, steady state voltage is going to vary depending on what that Q value is, and we can get a different result depending on which Q value we're working at. So these are the frequency ride-through tests, which are done by programming the source frequency, and the angle jump tests. These are done by programming the source angle in phase source table. And these are the control reference tests. So we're setting for each of those 4 step, control step reference tests, we're setting each of those 4 tables, not to flat, but to some stepped value, depending on what the test is. And that is one function for each of the test suites that can be done from this script. And this is a utility function that loads all the interfaces. So it's going to look for all the components that we need to know by name. If none, if something is missing, it's going to tell you which one is missing and set this be failed flag to true, and then it's going to quit. Right. So if you get an error there or a message there, you need to make sure that the names match what the script is looking for. And this is set up to run, it loads the interfaces. If it finds the Solar 5 project, it is going to run each of these 6 test suites, one after the other. And it takes many minutes. My laptop isn't all that new, but it takes about an hour. So your mileage will vary, but it's not something we want to wait for now during the video. So to run that simulation, you would just do Python space plantscript.py as we did before with the fault script. And assuming that's been run, I opened the cplot5 Jupyter notebook to do the plots. I'm going to run the first cell, loading in all those case names, mnemonics, and these are the test suites that I can plot. That's the load channel function. This second cell is going to import matplotlib and set up some comparison plots that I want to run the compare each test suite. This support function runs processes and plots one test suite, so I'll enable that, compile it. We're doing PSCAD import. Again, you check your path to where you unzip these files. If you ran the case yourself, they should be there. And then so we will process one of these test suites. Do the I think the undervoltage ride through test is the first one. There's some typos here that I'll correct. You'll see that these labels will be corrected by the time you get to run this. But what it is doing is reading. I think there were 15 undervoltage ride-through tests, so it's reading 10 channels out of each of those files. It takes several seconds. And then when that's done, we're going to get a plot of all of them. So this plots for the solar plant each of the 15 cases. The legend is going to be over on the right. Just barely fits, of course, but in some cases it rides through, and in other cases it may not. Well, actually, there are some some things to dig into, like the the initial power level to satisfy yourself that it's all correct. But for example, this one here, that power level only reached 0.6 per unit, where we were either we wanted it at 1 per unit. And so the reason it didn't get there could be due to excessive voltage drop because of the weak grid condition. So that is something to be checked into. It could be a model. It could be something to do with the test condition. It did ride through. When the fault is applied and cleared, it did ride through. But this behavior here before the fault isn't exactly as inspected. So if you were going to receive a model like this, you'd want to know what was going on there.